All right, so we're going to go over how to predict products for chemical reactions. This is for, or originally was for, Dallas Center Grimes, Unit 5, Part 1. Okay, before we begin, get out these two different things. You need to have your periodic table as well as your polyatomic ion sheet. If you don't have access to those two things right now, I put some links in the description so you can have electronic versions of that for when you go through this. But if you don't have those two things, you're going to get really lost really fast. So that is crucial that that information or those materials are available to you. Before we get into how to predict products for chemical reactions, I wanted to reintroduce what a chemical reaction is and what it looks like and some important parts of it. So first of all, a reaction is a model that we use that takes the different chemical elements or chemical compounds and shows what happens when you put them together. These are going to be the reactants. This is going to be the before the reaction. Reaction occurs, and these are the products. That's what happens afterwards. So we have reactants and products. We have two different parts of this then as well, two different kinds of numbers. We have these larger numbers out front, and then these smaller numbers down here. The larger numbers out front are called coefficients, and they tell us how many there are of this chemical compound. Another way to do this, instead of putting 2 NaI, would to say that I had an NaI chemical compound and another one. This is shorthand to say that I have 2 of those. The subscripts tell me how many of that specific element there are. So in this case, I have 3 oxygens and 1 nitrogen in this nitrate molecule. Now this guy right here is called a polyatomic ion. Polyatomic ions are packages of elements that stay together in a chemical reaction. You're going to see the exact same thing as a reactant as you do as a product. And the different polyatomic ions that we use are on your polyatomic ion sheet. A really easy way to identify polyatomic ions is based on parentheses. If there are parentheses, then the thing inside is a polyatomic. Sometimes, though, when there's only one of that polyatomic, you won't see parentheses like this. So another way to do it then is to look that you will always have 2 parts. So in this chemical compound, those are 2 parts. We have sodium as our first element, and then we have nitrate as our polyatomic ion. The first element will always be a metal like this. If you have a polyatomic ion, the one exception is the polyatomic ion ammonium, and that's NH4. And if you see that, that is also a polyatomic ion. All right. The different reaction types. This first reaction, we have 2 individual elements forming one single compound. This is called a synthesis reaction. The opposite of a synthesis reaction, where you take one chemical compound and form 2 smaller compounds, or 2 smaller elements or compounds, that is called a decomposition reaction. If we have a single element right here and a chemical compound, this is going to tell us that it's a single replacement reaction. This metal, it's always going to be a metal, is going to replace the cation in the other chemical compound. So we can see that if we, on the product side, we have copper by itself now. So there's the copper, that's the metal by itself. And then aluminum is with the polyatomic. This is called a single replacement, because we have a single element replacing another element in a chemical compound. The one that looks the most confusing is going to be double replacement. This is when the cation of one chemical compound switches with the cation of another chemical compound. So we have to identify the two different parts of the chemical compounds. There's one and there's one. Again, it's always after that cation, and it's the single element. It's listed here, and it switches places. So on the other side, silver is going to be with chlorine, and iron is going to be with the nitrate. The last kind is going to be when we have a carbon-containing compound reacting with our oxygen. When that happens, we always are going to produce the same products, carbon dioxide and water. And this is a combustion reaction. This combustion reaction right here is what is used to heat most homes in the United States. This is methane, or natural gas, reacts with oxygen to produce those two products as well as heat. Now when we predict products, actually I'm going to go back to this just for a moment. Notice that these are all balanced, meaning they have those coefficients out front. But in this video, we are not going to be looking at how to balance these chemical reactions. We're going to work on how to predict the chemical formula for the product. For example, if we go to the single replacement reaction, how did we get the 2 here and how did we get the 3 here? Or how did we get the 3 there? Or why is that 2 there? Why did that 2 go away? All of those. The reactants stay the same. So these always stay the same. It's the products that have something that we have to do work with, and we have to predict those subscripts. So that's what we're after in this video, not how to balance. All right. So we have the different, some different practice of chemical reactions. Now, since we're after predicting the products, we actually have to be able to identify these different kinds of reactions just based on the reactants. So if we go through this process, just like we did before, we can start identifying what's possible, and that helps us determine what the product is going, or what the reaction type is going to be. For example, this is a single chemical compound. The only thing that it could possibly do is to split up into its 2 different elements. This is going to be a decomposition reaction. It breaks apart. This one, we have this messy work here, all of these different things. So we have a chemical compound here, a chemical compound here. Again, I'm drawing that line there to distinguish the 2 different parts of the chemical compound. This is going to be our cation, this is going to be our anion. And when that happens, these cations are going to switch places. And if we have 2 different cations switch places in a chemical compound, this is going to be our double replacement. Carbon-containing compound reacts with oxygen, combustion. Single replacement element here, or single element here, reacts with a chemical compound. And so if we have zinc replacing iron in this chemical compound, this is going to be our single replacement. The last one here, we have 2 different elements combining together. When that happens, we get a synthesis reaction, the opposite of a decomposition reaction. All right. Sorry about that. All right. So let's work on predicting products. In each of these different cases, we have the type of reaction we're going to look at, and then some guided practice, and then you have some practice to do as well. Synthesis reactions occur when we have two different elements forming one single chemical compound. And to do this, we want to write out what that chemical compound would look like without any subscripts. If you bring the subscript over, chances are you're going to be wrong. Maybe you'll get lucky, but oftentimes that does not occur, where the same subscript is on both sides of the chemical reaction. So we don't want to carry that subscript over. We just want to start with what's called the skeleton. Then we use the charges to figure out these subscripts. Since aluminum is a +3 and chlorine is a -1, this comes from the periodic table. Again, if you're not sure where that comes from, there is a periodic table with that information on it in the description section. That does not equal 0. And whenever we're forming a chemical product or chemical formula, we want the overall charge to equal 0. So since this does not equal 0 yet, we have to change the subscripts. So if we take 1 aluminum and 3 chlorines, now we have 3 things that are -1, a +3, and a -3, because there's 3 of them, does get us to 0. And that's what we're after. Another way we can do this is called the crisscross rule. So if we ignore the charges here, get the charges from the chemical or from the periodic table, the value of that charge, so the 3 becomes the subscript for the chlorine and the 1 becomes the subscript for the aluminum. Let's see how that works for the next one. We have potassium and sulfur. Here is potassium sulfide. That's the only thing that we could possibly have here. There's a +1, -2. Again, that information comes from the periodic table. The 2 comes down and the 1 comes down. And that becomes the correct chemical formula. Calcium oxide, we have CaO +2 -2. The 2 comes down, the 2 comes down. When that happens, though, we end up with Ca2O2. We want to reduce CaO. So that becomes the correct chemical formula. This is the reason why I don't often teach it this way. But if you just remember to reduce, then the crisscross rule always works. All right, why don't you try 3 of these on your own? Get out your periodic table. You don't need your polyatomic ion sheet for these, and come up with the correct formulas for the products. Again, the reactants always stay the same. The only thing that we're after here is producing the correct subscripts for these products. I'm going to put up the answers here very shortly, so this is the time for you to pause this video so you can get these done before you go on. The answers are coming in 3, 2, 1. Cesium is +1, iodine is -1, so we end up with CSI. Aluminum is +3, sulfur is -2, so the 2 comes down, the 3 comes down. The rubidium is +1, the bromine is -1, so we end up with RbBr. If you happen to write this, please change it to this. We always write the metal first. The cation gets written first. This is not correct. So that would not be accepted. So switch those around. All right. Let's go on to decomposition, which is the opposite. This one is just a little bit more difficult because of something called diatomic elements. Before we work with those diatomic elements, though, let's just go ahead and split these things where they're going to decompose. It always decomposes between the first and the second element, so we end up with iron and oxygen. In this one, we end up with silver and chlorine. Here, we end up with hydrogen and oxygen. Notice, again, I did not bring any subscripts over. When we have an element all by itself like this, it doesn't have a charge. We use charges to figure out the subscripts in a chemical compound. Since it's not part of a chemical compound, no charge. In order to figure out the subscript on a single element, we have to use the 7 diatomic elements. If it's one of the 7 diatomic elements, it comes as a pair. If it's not, it just stays the way it is. And the 7 diatomic elements are these: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and then over here we have hydrogen. I wrote them like this because it's similar to how they are organized in the periodic table, and it helps us remember which is which. Remember that there are 7 diatomics, and then we go to the periodic table and we find out that nitrogen has the atomic number 7. So that makes it easy to start with one of them. Now if we make the number 7 on the periodic table, that takes care of 6 of them, which is kind of annoying, but the last one is going to be hydrogen. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine are 6 of the 7 diatomics. The last one is hydrogen. So if we look at a chemical or an element like iron, which is not one of the 7 diatomics, it stays the way it is. Oxygen, since it is one of the 7 diatomics, becomes O2. Silver, not on the list. Chlorine is on the list. Cl2. Hydrogen on the list. Oxygen on the list. So again, when you have an element by itself, you don't think about charges. Instead, you ask yourself, is it one of the 7 diatomics? Try some on your own. Now, ladies and gentlemen, I want to emphasize here, if you are practicing these and actually trying to learn this information, this is the time that you pause the video so that you can practice them and then get the answers in check. Do not just watch the video and wait for the answers to come up. That's not doing you any good. So pause the video. Answers are coming in 3, 2, 1. There we go. If we look at these, zinc, iron, and rubidium, first of all, we split them in between the 2 different elements. Those are going to be our non-diatomics, where oxygen, chlorine, and iodine are all on that diatomic list, so they are O2. Single replacement reaction. These are a little bit more difficult. We have sodium switching places with the cation. And this is always going to be the same thing. The element by itself is going to switch places with the element that is the first element of the chemical compound, the cation. The cations will switch places, so we have magnesium switching places with nickel and barium switching places with tin. Go through and write out the chemical formulas without any of the subscripts. And right now you might say, but Mr. Mengler, you just wrote a subscript there. Remember that if it's a polyatomic ion, it is a package that does not split up. Therefore, the subscript is the same thing on both sides. These are going to be that exception to the rule that we don't carry subscripts. So we have Na2 or NaSO4, and then we have hydrogen all by itself. Come up with the correct chemical formulas. Sodium is +1. Sulfate, SO4, is -2. Again, this is going to be on your polyatomic ion sheet. That is one thing. Bring the subscripts down. 2 there, 1 there. And we don't show the charges when we're done. Hydrogen is an element that is all by itself. We have to ask ourselves, is it a diatomic? It is, so it's H2. Same thing here. Potassium goes with the phosphate. And then we have cobalt. Look, and again, I can't emphasize this enough. This is the mistake students make. The 3 is here. It does not get carried over. Those subscripts do not get carried. Same thing for this 2. The 4 does because phosphate is a polyatomic ion. Potassium is +1. Phosphate is -3. Crisscross. There's the K3PO4. Cobalt, not one of the 7 diatomics. Therefore, it stays just as cobalt. These guys switch places. We end up with MgBr plus nickel, +2, -1. So there it is. Nickel is all by itself. Get rid of the charges. Don't need those in our answers. Barium goes with the nitrate. and tin is by itself. Barium is a positive 2 charge. When it forms ionic compounds, nitrate is -1. So we have to have that. And this is the first time where we had to use parentheses. If we have more than one of those more than one of those polyatomic ions, we have to show parentheses, and then the 2 goes outside. All right. Again, try them on your own. Make sure you pause the video here. If you are not pausing the video and trying these, do not bother coming in for help. Answers are coming in 3, 2, 1. And here they are. Aluminum is +3, chlorine is -1, copper is not a diatomic, barium is +2, hydroxide is -1, aluminum not a diatomic, magnesium +2, nitrate -1. There's that 2 outside the parentheses again, same thing with the barium hydroxide, the 2 outside the parentheses. That hydroxide is kind of confusing because it looks a little bit different than the other polyatomics, so we just kind of have to remember that that's one of them. And then here we have lead and sodium nitrate. Notice there are no subscripts on these because sodium is +1 and nitrate's -1. So that doesn't go away. All right, and maybe I'll just do one of these because you might still have this question like, well, where did this 2 go? Well, remember, ladies and gentlemen, once we have the correct chemical formulas, we balance. So we have a 2 there and a 2 there. The coefficients go in front to take care of that. Double replace it. This is the one where we have 2 different chemical compounds, and we have 2 different chemical compounds like that. It's the cation that switches places. So the magnesium is going to switch places with that nitrate, or with the sodium. Magnesium and sodium will switch places. Here's magnesium nitrate. That is a 3. Boy, let me see if I can get my handwriting to work a little bit better. Here is magnesium with the nitrate and sodium with the oxygen. Charges, I'm going to leave the charges up here as we go. This is +2 and -1, +1 and -2, so we have to add subscripts because that does not cancel out. 2 there, 2 there. Here we go. Iron hydroxide. Then we have calcium chloride. I'm going to do this one first and come back to this one for a reason. Calcium is +2 from the periodic table. Chlorine is -1, so we bring the 2 down. Calcium chloride. This one is a little bit more difficult because you cannot figure out the charge on the iron from the periodic table. However, whatever charge that it starts with in a chemical compound is going to be the same charge that it ends with. So if we can use information on this side of the reaction to figure out its charge, we know what it is over here. Since we know that chlorine is -1 and the overall charge of a chemical compound is 0, since there are 3 of those things that are -1, that means that the iron must be +3. Because +3 and 3 things that are negative makes 0. That means that our iron is also +3. There I go. Aluminum with the copper, we end up with AlNO3 and CuPO4. Charges, aluminum is +3. Nitrate is -1. We know that nitrate is -1 from the polyatomic ion sheet. That's how we knew it up here as well. Make sure you have that out in front of you. Crisscross, we need to have 3 of these nitrates, copper and phosphate. Copper in this case is going to be +2. Why? Well, we know that nitrate's -1. Since there's 2 of them, that means that copper has to be a +2. +2 on that side, +2 on that side. Phosphate from the polyatomic ion sheet is -3. So there's 3 and there is 2. So there you go. Try these on your own. One more time, guys, if you're going through this video and you do not pause and try them on your own, you really shouldn't be coming in for extra help, because this is where that help is coming from. Do them on your own, pause it, then the answers are coming up in 3, 2, 1. We can look at the charges here and determine how we got the chemical formulas. Again, make sure that we switch places, potassium and calcium. So this is +2 and -2, +1 and -1. Notice that 3 down here, that subscript stays because carbonate, CO3, is a package deal. So 1 calcium, 1 carbonate. Here we have, this is that ammonium here. Let's look at this one a little bit more carefully. That's where this thing splits up. So we have a cation replaces the cation. This is the only positive polyatomic that we have. And those two are going to switch places. The cation with the cation always switch places. So we have sodium here with the +1, carbonate with the -2. Ammonium is that name of that one, and then -1 for the chlorine. So that's how we got that 2 there. All right, silver with barium, silver hydroxide over here, +1, -1. I know that here, -1 for the nitrate. That means that silver must be +1, and it stays the same. Barium is +2, nitrate is -1. The 2 comes down, and we have that. All right. I actually just realized I have not done the 5th kind, which is going to be our combustion reaction. And so I am just going to go ahead and do a blank one right here and do a couple by hand, because these are the really easy ones. Anytime we have a carbon-containing compound reacting with oxygen, we get the same 2 products, carbon dioxide and water. This again is the combustion. This is the one that is the easiest of all of them, but the one that I think gives students the most difficulties. The reason is that you will see a problem where it looks like this. Oops. Without any products, and you try to think, oh, well, it's a single element, it must be a singular replacement reaction. Remember, though, that if we see that carbon-containing compound, this guy right over here that I'm erasing on, this is going to tell us that it is a combustion reaction. And if we know it's a combustion reaction, we don't have to do anything with charges. We don't have to figure out any kind of subscripts. We don't have to do any extra work. All we have to do is to write out these 2 products, carbon dioxide and water, and you'll be done. All right, ladies and gentlemen, there you go. Hope this helped.